This is the video for section 4.5 on linearization. This section includes some information about Newton's method, but we are not going to do this. Linearization will show up on the AP exam, so this is a good kind of coverage of that. Linearization formula is L of x equals f of a plus f prime of a times x minus a. If f is differentiable at a, then the equation of the tangent line is above. So we're back to equation of tangent line. So if you remember, we used point slope form before. Well, this is essentially the same thing. Y plus m times x minus x. We have our y1, our x1, and this is our original y. We can see point slope form already showing up here. So we're back to first derivative gives us the slope of the tangent line. Alright, so if we start with our first example, find the linearization of f of x equals the square root of 1 plus x at x equals 0. Use that to approximate the square root of 1.02 without a calculator. So first we want to find our linearization. Remember our formula is L of x equals f of a plus f prime of a times x minus a. Alright, so if we set things up first, we know we have f of x. Let's find f prime of x. Well, we know f of x is 1 plus x to the 1/2. So it's going to be 1/2 times 1 plus x to the negative 1/2 times the derivative of the inside. So the derivative of x is 1. So that's going to give us 1 over 2 square roots of 1 plus x. Okay, so we're finding the linearization of f of x at x equals 0. So 0 is our a. Alright, so f of a, so if I plug 0, if I start out, f of 0, I get the square root of 1 plus 0, which equals the square root of 1, which equals 1. So f prime of a, prime of 0 equals 1 over 2 square roots of 1 plus 0, which equals 1 over 2. Then I go to my formula. And we're going to say L of x equals f of a, which we said was 1, plus my slope, which is 1/2, times x minus 0. And I get 1 plus 1/2 x. That is my linearization formula. Now the question says to use that to approximate the square root of 1.02. Now to do our approximation, we're going to use x equals 0.02. Because we already have the 1 here, that accounts for the 1 in the function over here. We see these two together. So when we go to do our approximation, we're going to find L of 0.02, which equals 1 plus 1/2 times 0.02, and this all gives me 1.01. If you type in your calculator the square root of 1.02, you will get 1.00995, which rounds up to our approximation of 1.01. So linearization helps us to find, using the tangent lines, then we can find other values and see how close we can get. Let's look at another example. Find the linearization of f of x equals the cosine at x equals pi over 2. Use it to approximate the cosine of 1.75. So we start out, remember L of x equals f of a plus f prime of a times x minus a. Remember in this case a is pi over 2. So f of pi over 2 is going to be the cosine at pi over 2, which equals 0. We find f prime of pi over 2. Well, f prime, the derivative of the cosine, is negative sine x, which equals negative sine pi over 2, which is going to give us negative 1. So L of x equals 0 plus negative 1 times x minus pi over 2, which results in, if I distribute my negative 1, negative x plus pi over 2. So in this case, we're trying to approximate the cosine of 1.75. So we're going to do L of 1.75. Which equals negative 1.75 plus pi over 2, which is going to equal negative 0.179. Well, when we do this in our calculator, we get the cosine of 1.75 to be negative 0.17824. So we're pretty close with our approximation. Next thing we're going to talk about is differentials. When we talk about differentials, we're talking about dy equaling the first derivative times dx. So what happens here, we're going to use this a lot come the next unit, is sometimes we're given x and dx is the change in x. So if we know these values, we can actually find a value for y based on the differential. So in our example here, we know we need to find dy and evaluate for the given values of x and dx. So y equals this, dy dx equals 12x squared minus 3x to the negative 2/3 dx. And what happens here is now we're going to plug in 6 for x and 0.5 for dx. So we get 12 times 6 squared minus 3 times 6 to the negative 2/3, and then that whole thing gets multiplied by 0.5. And we're going to type the whole thing in our calculator. This equals 215.546. So now we can get an actual value for our derivative. Try again. Now here you have a couple of options. You can solve for y first and then find the derivative, or you can use implicit differentiation. That's totally kind of up to you. So if we try solving for y first, we can add x to both sides. Y plus xy equals 5 plus x. Factor out a y. 1 plus x is 5 plus x. And I end up with y equals 5 plus x over 1 plus x. Here, I now have to do a quotient rule, where u equals 5 plus x, v is 1 plus x. So du is 1, dv is 1, and I get dy equals v du, so 1 plus x minus u dv, 5 plus x over v squared. All dx. So dy equals, if I combine the tops, I get 1 plus x minus 5 minus x. And my x's are actually going to cancel out. I have a positive x and a negative x. So negative 4 over 1 plus x squared dx is my differential. Now plug your values in. So dy equals negative 4 over 1 plus 0 squared times 0.002. If I type that whole thing in my calculator, I get negative 0.008. That's the value of my differential. So if we take a step back for a second, when we think about differentials, we know that dy dx is the same as the first derivative of x. Well, all we're doing is we're taking this dx part and we're multiplying both sides by dx to get dy by itself. So that's what's happening here. Then we can use that change in x to help us solve our problem. So moving forward, your homework is page 242, 1 through 7, and 19 through 26 all. The first 7 are linearization problems, and the next ones are differential problems.